So here is another topic, and this is more general. And again, this one we try to calculate the distribution of the stress in we call the bar or in the elastic material. And in particular, this cross section. In this section, we want to study. We pick up any cross sections, any cross section in any orientations. So maybe the better way to demonstrate is I leave the slides here for comparison, then I will redo everything starting from here. So we consider elastic material, and this one, again, at the two end is under uniaxial loading, and the magnitude equal P. So under this case, this is in static equilibrium. Okay, so now come to the end is here. Our concept is this stress, again, is equal to force divided by cross-sectional area. So here we come to the two kind of reference for us to proceed. One is we need to identify which cross-section we're interested. So I think the easiest way is this. For example, if you like, you can pick up the cross-sectional area like this one. So let me say this is a cross-sectional area. Let me call it A. Here is A0. Okay, so for the first scenario, say this is a scenario 1. So in this area, in this one, then we can pick up the free body diagram. So here, this is the cross-sectional area. So this is a force, and on the free body diagram, then I'm going to use the red color imbalance. This must be equal to force here, F. So therefore, on this cross-section, we would have the stress. The stress, this is normal to the cross-section. So with this one will induce normal stress. So we use sigma. And that magnitude equal to F divided by A now. And for this case, that is tension. So that is what we have done before. Okay, and now we can pick any cross-sectional area. So in more general, the second option is this. Let me pick this one. And rather than the vertical, I pick up the inclined. And you could ask me why you pick up the inclined and give us certain travel time, the hard time. For demonstration, this is more generic. Okay, so here and these inclinations, and I just here follow up our textbook notation. Here inclination measured orientation is theta measured from the vertical direction. So theta is measured from here. Okay, so under these situations, and again, we want to know what is the force, what is the area. So let me pick up the cross-sectional area, the free body diagram, and here is our inclined plane we pick. And remember here, this is our theta here. Okay, so this one is the force here, F. So now here in this inclined plane, and the first one, let us fix the area. So now this has the area A now. So let me put into this triangle here. This is our inclined plane, and this side is A now, and this is theta. So what is the area here? Assuming they have the same uniform thickness out of board. So basically the area for this case, this is proportional to the length of the sides. So therefore from here you could imagine this one should be equal to A now divided by how much? Cosine theta. Are we good? Mm-hmm. Any questions? Mm-hmm. Should be okay. Okay. So this is about the area. And now let's focus on the force. So now let me draw the force here. So this is an inclined plane. And here I pick a free body diagram. Basically this force being transmitted to here. So this is the force here, F. And this is the theta. So on this inclined plane, and we try to follow up our concept. We wish we can decompose or we can calculate directions on the inclined plane. One component is normal. So let me call using the notation the same as this. So let me call this is a normal to the cross section P normal. And the other one is, let me say, the other component is called the P parallel to the cross section parallel. Okay. So the two components are the direction. In particular, I project into one is normal, one is shearing, one is parallel. So in this way, these force components will induce normal stress. This force component will induce shear stress. So by picking up an inclined plane, before we do the calculation, right away we should recognize right away is, as compared to this cross section, which will only give us the normal stress. Then for the inclined plane, not only we will have the normal stress that is induced by P normal, but also we will have the shear stress. And the shear stress is induced by this component. Okay, before we do the detailed calculation, we should have this recognition. Okay, so this is about the force. So you see right now we have the area, we have the force components. So we simply divide each force components to area, then we will get the normal stress or shear stress. So that's the concept. So the detail is we simply implement the whole calculations. So to calculate the normal stress component and the parallel this force components, and then we simply use the equilibrium equations. So let me say this is the, I just make it arbitrary. So for example, say in parallel, in this one, let me call the force in parallel direction equal to 0. So that means in this component. So here, for this component, we can project into, let me enlarge this one here. So this is theta. So this component is how much is F cosine theta. This one is F sine theta. Okay, so this one is this one here, this one here. So by force equilibrium in the parallel in this direction equal to 0. So from here you can see this component must be equal to this one. Got it? So therefore P parallel equal to F sine theta, and then in the other directions, so P normal equal to F cosine theta. So let me write it up here. So this one equal to F cosine theta. This one equal to F sine theta. So now we have area, we have force, then we are able to calculate the stress. So the normal stress, so here let me re-express the Fibonacci diagram again. So the first one, let me determine the normal stress. Normal stress will be equal to the P normal divided by area equal to A now divided by cosine theta. Right? Okay, and then we simply plug in. P now is F cosine theta divided by A now cosine theta. So here we do the symbolic calculation, but in homework, in exercise, we are given our numbers. So basically, it depends on each conditions, you work on the numbers. So for this case, it's A divided by A now cosine squared theta. Okay, so this is for the normal stress, and then for the strain stress, tau is equal to P parallel divided by this one. So that P parallel is F sine theta divided by A now cosine theta. So this one is F A now sine theta cosine theta. So that is the result we come up with at this end here. And by plugging into, this is a formula for trigonometry. I think 8th graders should be able to learn this one in next year in the 8th grader math, I hope.
In which math?
The 8th grader math or algebra,
Okay.
I think. So here, basically that is a formula. So we plug in, so my next step is, for this term, I'm going to replace by this formula. And then for this one, I'm going to replace by this one for an easier seeing what's going on there. So basically here, that would be equal to F A now, and cosine squared theta becomes 0.5 times 1 plus cosine 2 theta. And then this one becomes F A now, and this one becomes 1/2 times sine 2 theta. So for this case, we can see if you know how to run programs and write simple program, for example in MATLAB, and simply you can write this. You can draw, for example, theta equal to from 0 to 90 degrees, and then here you show the magnitude of the stress, and you can get a curve like this one. So for this case, the normal stress is in terms of this one. So the normal stress will become maximum when cosine 2 theta equal to 1, and the normal stress will become 0 when cosine 2 theta equal to -1. So from here, this kind of the result can give us certain parametric study about, okay, in which orientation, what kind of the stress we would have, and how big each stress component we would have. Okay, so here in this section is pretty much general, and then if you wish, you can plug in the numbers, and then yeah, just give a try. And so that is the purpose of this section. And to me, my suggestions to you, and just treat this section as the symbolic calculation of certain general examples, and don't need to memorize those equations. I don't think that is useful. And in our the test or final exams, or in any exams, I will prepare the cheat sheets. So for everyone, you don't need to memorize all the equations. All the equations should be available on the cheat sheets, or you can ask me during the test. Okay, so the critical things for you and for my goal is to guide you to the right thinking process, to the appropriate calculation steps, and that's the whole thing. And so I think that's it. And that is for the section here. And those are the summaries of the details, and that should be very straightforward. And for this page, just show you when theta equal to 0 degrees, we will have the maximum normal stress. And when theta equal to 45 degrees, we would have the maximum strain stress. And those things is not so particular, because here we can just play around by programming. We can see the whole thing. Okay. And that's it. Thank you.